So, Mr. D, what's your favorite food?
Clearly, I'm a connoisseur of favorite foods, but lately I've been really enjoying calzones.
Oh yeah,
How are you?
Italian. Yeah, yeah, Mexican food. Moving to Texas. I'm in heaven. Oh my gosh, yes. Okay. Today, folks, we're going to talk about two sort of big topics, and the two big topics are kind of how we deal with numbers, how we think about numbers, and then how we count something called significant figures. So, there's this concept of accuracy and precision. All right, two different terms, best illustrated by this image that we see on the screen. So tell me about the first image right there. What would you say about that one, Mr. D?
Well, you look there. If we're trying to hit the bullseye in the middle, we're not being very accurate, are we?
No, no. In fact, that's we would say that's not accurate and not precise because nobody hit, no one's close, right? And they're not even close to each other, right?
By the way, precision is kind of weird because you sometimes think that accuracy and precision is the same thing. Precision is how close you are to agreeing with your measurements. So you can be precisely wrong, which is exactly what happens if you look at the second diagram. All of those targeted are very close to each other. So they all agree with each other, but they're wrong.
So maybe a good example of something that's precise but not accurate is, let's say that you have a bathroom scale, and that on a lot of bathroom scales, a little knob. And maybe if you want to do a joke, maybe one of your parents is trying to lose weight or something like that. If you go and you adjust that, and you adjust it like 6 or 7 pounds heavier, it's a good joke. Don't do this. They're going to step on that balance, and they're going to say that they're 5 or 6 pounds heavier than they think they are every single time. So that's precise, but it's not accurate because you've been monkeying with the scale. So that's precision versus accuracy. And when we really want, obviously, something that's both precise and accurate, you can't have something that's precise unless you have multiple measurements. And so we usually believe that if we can measure something multiple times using good measuring devices, that we're going to get an accurate answer. Isn't always the case. It depends on the devices that you're using to measure them. So that leads us to how do we know something is accurate or not? Let's watch this video.
All right, we have Mr. and Mrs. Gummy to help us out to understand why we use significant figures and why does it matter what tool we're using. So we're going to put them on Mr. Jenke Balance over here. And when we put it on here and we measure the mass, oh, he fell over, that's fine. We end up with a mass of about 6-ish or so, 4.6. I cannot say anything more accurately than that because this only measures 0.2 of a gram. And I take it on to the slightly better and more electronic balance over here. If you take a look at it, this now says 4.59. So we've gained a little bit of accuracy, right? And then we put it into this only special people VIP measuring for gummies. And we put it onto this. This measures to 10,000. We even have to close them in there so there's no air current. If you take a look here at the actual mass in this one, it measures to 10,000ths of a gram, 4.5910. Has the mass of these two gummies changed from the first scale to the second?
Yeah, no.
I would argue no, right? So what has changed? Well, the amount of accuracy that each of these scales, from very poor to not so bad to, oh my goodness, I want to marry you level of accuracy, has changed. So that's where significant figures come in, because there's no way I can say, like I did over here, 4.5910 on this scale. So if I write 4.5190 in my notebook, I'm going to believe that you used this guy, not this guy.
So, Mr. D, what's up with this statement here? We use what?
Significant figures.
Significant figures, all right, sig figs is the term we'll use for shorthand, to indicate that our measurements are accurate, right? So when we have to record a measurement, we must always include the numbers, right, that we know with what?
Certainty plus one uncertain guess.
Okay, certainty plus one uncertain guess. So let's draw a picture. Let's say that I have a ruler here. And let's say that this is 5.0, and then this is 0.1, 0.2, 0.3. And I've got a something I'm measuring right here, some rod or something like that. And so what would be this measurement? What would you say this measurement is?
Well, we always go to the smallest gradation on a tool. So if we count over, wouldn't the 0.3 be the smallest gradation that we know for certain? We know it's.
So we know that this is going to be 5.3, but that you said a minute ago plus one uncertain one. And so what would you guesstimate that your last one is?
Well, here's the beauty of a guess. It's going to be somewhere between 0.3 and 0.4, right?
Yeah.
So I'm going to say it's 0.6. So it's 0.06. So we'll put a 6 in there, right?
I honestly think it's more like 5.37, honestly, as I look at it. But,
And-
I mean,
And here's the thing: I could have said 0.30. That's my guess. I do whatever I want with that guess, and so we always understand whenever we're reading a tool of any kind that very last number, that's your guess.
that's right. All right, so we want to go one level past the measuring of the device, if it has that. If it's a digital device, you're not going to have that option. But if it's some kind of an analog device, you can always make that guess on the last digits.
And if it's digital, they make the guess for you, so you don't have any option with this.
So this leads us to an interesting question. When we're talking about accuracy and precision, we want to talk about this thing called sig figs. Ultimately, there are 4 sig fig rules, and let's just write the rules down. So the rules, write this down, folks. Rules of sig figs. So here we have 5 rules, right? All non-zero digits are significant, leading zeros are not significant, captive zeros are always significant, trailing zeros are significant if a decimal is present, and exact numbers have infinite number of significant digits. This, you might be going, what the heck are they talking about? I thought numbers were numbers. No, they're not, because they represent measurements. Like we've been talking about, you saw in the video, right? We had the gummy bears, and the gummy bears had the same mass every time we put them on the different scale. And so we want to indicate how well we know their mass, or whatever it is that we're measuring. So what we want to do is just do several examples, and what we want to learn is how to count significant digits. Does that make sense? So let's say I have the number 1781. I'm going to break a rule here and not use units, okay? 1781, how many significant digits? Notice there's no zero. So Mr. D, what would you say? How many significant digits?
That would be 4.
Yeah, just simply 4. That's super easy, right? Or 37.5. I've got a decimal, but there's no zero. So 1, 2, 3. It's just significant digits, right? Understand the idea of digits, right? Or if we have something that's exponential, 5.342 times 10 to the third. Now this is a little tricky. You have this third here, but we just ignore, if we've got something in scientific notation, we just ignore that. So that's just going to be the number of digits there. They're all non-zero, so that's 4 significant digits. Make sense?
Matter if it's a decimal?
No, not in this case, because there are no zeros. It might if there are, well actually no, because if there is a decimal, yeah. Well, a decimal does matter. There's a doesn't matter. So let's talk about where's a different one. 1002. Now here's what we have. We call these captive zeros. See how these zeros are caught between the 1 and the 2. And what's the rule on captive zero? Rule number 3, they're always significant. So that's 4. Because those zeros count. Does that make sense? Or if I have 30.02, again, both of those zeros, that's a 0, is 4 as well, because those zeros are captured between the 3 and the 2. The trick comes when we get to problems like this. If I have 300, so 300 has what? What kind of zeros are those?
Those are trailing zeros.
Trailing zeros are significant if a decimal is present. Do you see a decimal? No. That's just 1 significant digit. That means basically the measurement is from here. So like I'd say, the distance from here to Dallas is 300 miles. I bet that's neighborhood right, but it's just kind of a ballpark. It's not exactly 300 miles. Now there is a place that's exactly 300 miles from where I stand. But if that's the case, well, let's do this. What if I say 300 point? I have trailing zeros, but there's a decimal. That would be 3 significant digits. You're saying 300 is different than 300 point? That's exactly what I'm saying. Because this is a super accurate measurement, all right? Because you have a decimal present. Now the tricky ones I think most people struggle with is these ones. So this is called a what zero? I got 0025.
Leading.
That's a leading zero, and so those leading zeros, those are 1, 2. Do you see the deal is those don't count? So the only significant digits here are the 2 and the 5. So this has only 2 significant digits. That is one I think that trips people up the most. By the way, rule number 5 it has to do with when we do things like conversions. When we say that, for example, there's 1,000 milliliters in 1 liter, a lot of people will say that, wait a second, that there's only one significant digit. But this is like the definition of a liter, or of a milliliter. So it's like 1,000.0000. It's an exact number because it's an exact conversion. So this is an exact number, and this would have an infinite number of significant digits. Any other examples we need to give, Mr. D?
No, not at all.
All right, so folks, precision, accuracy, and how we figure out significant figures. And we'll learn later how to multiply and divide with them, but that's coming up next because you're awesome.